In this captivating video, we'll dive into the groundbreaking discoveries shaking the very foundations of physics. Join us as we unravel the black holes and the possibilities hinted at by the Penrose singularity theorem. From Isaac Newton's revolutionary insights to Albert Einstein's mind-boggling revelations, we'll trace the evolution of our understanding of gravity and its profound implications for the universe. But hold on to your seats because the adventure doesn't stop there. We'll explore the prospect of a universe without singularities, challenging everything we thought we knew about the nature of black holes. Could this be the key to unlocking the secrets of quantum mechanics and achieving a unified theory of the cosmos? Join this conversation by smashing that like button and sharing your thoughts in the comments below. What mind-blowing discovery in space science leaves you awestruck? Your insights could spark a stellar discussion that illuminates the wonders of the universe. Don't forget to subscribe to our channel for more captivating explorations of space's greatest mysteries. Let's embark on this space journey together and uncover the secrets of the universe. Many, perhaps most physicists were seriously uncomfortable with the idea of black hole singularities. And they got even more uncomfortable when, in 1965, British physicist Sir Roger Penrose showed that singularities really are unavoidable in general relativity. His Penrose singularity theorem, for which he won the 2020 Nobel Prize, claims that as long as an event horizon exists, so must a singularity. Perhaps the most important implication of the singularity theorem is to show that general relativity really is in fundamental conflict with quantum mechanics. If that's the case, then the only salvation from the paradox of the singularity is some greater theory combining quantum mechanics and general relativity in which the singularity will evaporate away as if it was just the bad dream of ignorant 20th century physics. But just recently, we've had a ray of hope from a completely unexpected direction. In a paper released in December, Roy Kerr, one of the greatest black hole theorists of all time, may have shown that we can avoid the black hole's singularity without quantum mechanics after all. In order to get to this radical new result, we need to build up some understanding, so let's refresh our knowledge of black holes and review the Penrose singularity theorem. Then, maybe we can decide if Roy Kerr really did destroy the singularity. Roger Penrose didn't exactly prove that singularities exist, not directly at least. He showed that paths in space-time have to stop inside a black hole. When something moves in space-time because of gravity only, it follows a path called a geodesic. This path through space-time minimizes the total distance traveled, combining both space and time. Before the Penrose singularity theorem, people generally thought that geodesics never end. An object might move along a part of a geodesic like a ball thrown in a curve, but the geodesic itself stretches endlessly beyond the ball's path. It goes forward endlessly into the expanding universe or backward to the start of the universe. Roger Penrose revealed that within a black hole, paths in space-time must come together and finish at the center. When space-time allows paths that don't stretch infinitely, we call it geodesically incomplete. Think of these paths as the grid lines on a map of space-time, creating a smooth but sometimes twisted surface where the rules of physics operate smoothly. Geodesic incompleteness indicates areas where space-time gets squeezed, leading to infinite points and the breakdown of physics laws. So the argument of Penrose was that geodesic incompleteness means singularity. But Kerr has an objection to the argument, and it depends on a subtle interpretation of geodesic incompleteness. So let's dig a little deeper. When Penrose talked about a geodesic being ended by a black hole at its center, he meant something very precise in terms of math. He meant that the geodesic parameter is limited, so the mathematical factor we use to track the progress of something along a geodesic stops. It's like reaching the southernmost point when you travel to the South Pole. You can't go further south once you're as south as you can get. For the geodesics that describe the paths of matter, the geodesic parameter is usually the proper time. That's just the time measured by someone moving along that path. So if the parameter for a matter geodesics is bounded, that would imply a singularity because there's no way to trace a flow of time through it. There's no meaningful way to define after the singularity in either space or time. These are dead ends in space-time. Now Penrose constructed his argument using the paths of light, not of matter, and it turns out the difference is crucial, as we'll see. However, the general argument that geodesic incompleteness equals a singularity was a convincing enough argument that for nearly 60 years, almost all of us agreed that pure general relativity demands singularities. Stephen Hawking even used Penrose's arguments to show that in pure GR, the Big Bang was also a singularity all geodesics, traced backwards in time, had to converge and end at one point. However, Roy Kerr wasn't entirely convinced, to say the least. Kerr, a physicist from New Zealand, formulated the Kerr metric in 1963, a mathematical representation of a spinning black hole. This marked the discovery of the second solution to the Einstein equations for black holes, 47 years after the Karl Schwarzschild solution. The Schwarzschild solution only covers the simpler scenario of a non-spinning black hole. Now we have good reason to believe that essentially all real black holes have some rotation, so the Kerr solution is kind of a big deal, as is Roy Kerr. And Roy Kerr vehemently disagrees that singularities exist, nor even that the Penrose singularity theorem has anything to say about their existence. Let's finally get to the heart of his objection. So I told you that geodesic incompleteness has been taken to mean that space-time paths terminate, which in turn has been taken to mean that singularities are real. But there's a catch to this argument. Penrose constructed his argument using a particular type of geodesic, the null geodesic. These are the space-time paths traveled by massless, light-speed objects. A null geodesic represents the shortest path between 2 points in curved space. So what does it mean for a null geodesic to terminate? It means its geodesic parameter has to be bounded and not increase forever. In the case of massive particles, we used proper time to trace these regular geodesics. But things traveling at the speed of light don't experience time. Their clocks remain frozen, and so proper time doesn't increase along a null geodesic. To describe the geodesic motion of light, we need a different measure. We use something called an affine parameter, which is a slightly complicated thing, but the main thing is that it increases in a nice, clean way to track progress along a null geodesic. There are theorems proving things otherwise. Would you like to go deeper with this conversation in the next video? Comment down below, and we will get on to the next part of this video for you. Apart from that, what are your thoughts about this exploration? Subscribe to Space Episodes for upcoming educational videos related to space science, and press the bell icon. Thank you for watching this video until the end.